Godātie kolēģi, laiks ir sākt. Dear guests and dear colleagues, ladies and gentlemen, it was my idea to invite Professor Amir Fahmi from Germany and organize this meeting here. And now I'm very delighted and very pleased to welcome you at this meeting at our Faculty of Material Science and Riga Technical University. It is my great honor to set this meeting in motion. And first of all, I must thank the Hochschulkantor for its work bringing this meeting from idea to fruition. And I think that the next speaker will be the representative of the Hochschulkantor, Eva Pranka. Please, Eva, the floor is yours.
Good morning, dear ladies and gentlemen. And in the name of the Baltic German University Liaison Office, I would like to welcome you all today here to our seminar, The Next Gen Materials and the Opportunities They Provide. And today we will open our event with a guest lecture titled Nanomaterials, New Dimension in the Next Generation of Miniaturized Devices of Professor Fāmi. And after that, we will listen to Dr. Drunka's presentation, Synthesis and Properties of Modified TiO2 Photocatalysts. But before Professor Fāmi starts with his guest lecture, I would like to shortly introduce him to you. Mr. Fāmi's research career began in 1999. With his diploma thesis about mutations of insulin receptor genes in patients with diabetes mellitus version 2 at the Technical University of Dresden. And as a postdoctoral fellow, he was member of the nanoscience group in the Department of Physics at the University of Nottingham in the United Kingdom, where he supported the EU project supramolecular self-assembly of interfacial nanostructures. And then in 2005, as a senior research fellow at the University of Nottingham, Mr. Fāmi established his own research group within the Nottingham Innovative Manufacturing Research Centre. He has achieved the status of Associate Fellow of the Higher Education Academy of the United Kingdom after completing the postgraduate higher education program with his outstanding portfolio on improvement of the teaching of nanotechnology for multidisciplinary small groups. And since October 2011, Professor Fāmi has been holding the chair of Material Sciences at the Reinas-Vālas University of Applied Sciences in Cleveland, Germany. And Professor Fāmi has also experience with the DAD and also with EU projects, so we have really an honor to have Professor Fāmi here today in Riga, and now the floor is yours.
I think we have to open this one. You have to put it somewhere. Thanks a lot for the kind introduction. I do appreciate. I'm really happy to be in Riga. I say my second home country, say. I am glad to be here. I would like to thank again the Hochschulkantor for organizing this evening. Professor Kambars for his kind idea to inviting me. I'm really happy about it. And I'm happy that there are many audience to come to my lecture. I hope you will enjoy it. Okay. Thanks again, and we hope to have you next time in Germany. Okay. Before I start my talk, I'd like to just attract your attention about devices. As you probably thought about it, devices getting smaller and smaller and smaller. If you think about it, in our daily life, we have a very nice small devices. Some of them, they are very nice. As you see, some of them, you have to be very careful if you're traveling around. But really, they are very interesting kind of devices. Just if you think 20 or 30 years ago, it was, if you have a look here, it was really huge devices. We was at this level. After a while, getting more, devices getting small, but human getting more bigger. But if you think about devices as well, in 60, you can see this is a computer. You can walk inside computer. That is quite in 60. NASA managed to bring 2 people on the moon with this kind of computer, which I'm pretty sure is even weaker than the computer what you have it in your mobile phone right now in your pocket. And as you see, after 10 years, we're getting smaller, smaller, 90, and in 21st century, even this kind of computer getting smaller and smaller and smaller. We are actually heading what we call it miniaturization. Things getting smaller. And if you think about small devices, there are only 2 strategies to do that. One strategy, you make inside the device things smaller and you start to integrate them together. Or you try to make one component, making many functions that you can making your device smaller and smaller and smaller. This is actually about my lecture today. But before I start, I like to just give you a little bit hint how to build smaller devices. We have actually 2 different approach, what we call a top-down approach. Top-down approach, you need a very nice, highly clean room, very clean. You have many steps. You do need actually very high sophisticated device. But at some extent, if you like to getting with the structure smaller and smaller and smaller, you can catch what we call it physics limit. You have dimension limits. If you need to make nanostructure or nanotechnology or different level of miniaturization, you do need to have high sophisticated devices, which is pretty expensive. It needs more time to do that. And of course, manufacturing costs money and many steps to make this kind of miniaturizing device. The other option to start to make devices that you can have the nanomaterial, you can have this another concept, what we call it bottom up. And bottom up, you start to work from smaller into larger. If we think about from smaller into larger, we start with nanostructured material. We have composition, putting this composition in well-defined structure. We have novel properties. This can be translated into functions, component, making many functions, then you can build this device. Of course, what we're having right now, large, with top down, as I told you before, we're getting from larger into smaller, that you can having the devices smaller and smaller and smaller. For this reason, I dedicated my research group. We are working at the interface between engineering, between chemistry, between different level of technology that we can work in nanotechnology. Right now, we're working more likely in nanoscience, but we are hitting in the new generation of nanotechnology that you can really translate the science what we're having into real application in many fields. For this reason, I like to speak today about nanomaterial, how to use nanomaterial in the next generation of miniaturizing devices. One important thing, if you think about technology and devices, we have to think about cost, manufacturing, and time. Therefore, I will like to present today new concept, or concept should be used in future. We're using what we call it self-assembly. I put my research group in this area to use self-assembly to make nanomaterial or nanostructure material at different dimension and length scale. My lab just here, right in the border between Germany and Holland. We are the last, almost the last city from Germany. We call it Kleve, small city. We're having a new established university. This is Reinas-Vālas Lietišķo, University of Applied Science. We are not really old, but quite we hitting into the cutting edge of technology at our university in the different faculty. Before I start, I'd like to give you a little bit hint what I'm going to speak about it. I'm going to speak about self-assembly, how to use self-assembly as powerful tools in nanofabrication, how to control a structure of two important composition, organic and inorganic, to make hybrid material. And I have for this 4 short stories to show you how to make one-dimensional nanostructures in or via self-assembly to make what we call it nanofabrication. At the end, I will conclude how self-assembly it works and how self-assembly is a powerful tool for the next generation of miniaturizing devices. Before I start with my stories, I'd like to give you a little bit hint about self-assembly and what is self-assembly and why self-assembly will be the next manufacturing tool for nano devices. As you see, we are actually learning from nature. Self-assembly has been used long time ago. It's a spontaneously reversible organization of disorder systems that we can put this buildings block in well-defined structure. The whole idea is about that you're having buildings block in nanoscale. You try to adjust or control what we call it the local interactions between these buildings blocks that we can have well-defined structure. This structure could be 1D structure, 2D structures, 3D structures, and all of this structure, by putting well-defined composition, we can have what we call it well-defined properties, or novel properties can be translated into many devices. If we think about self-assembly process, we copied it from nature, and we have 2 important parts. One we call static self-assembly and dynamic self-assembly. If we think about static and dynamics, we actually having 3 different categories. The first one we call it co-assembly. In co-assembly, it's very simple, putting 2 buildings block together, just wait, you will have a well-defined structure. Or we have what we call it directed self-assembly, where we have to use well-defined driving force. In this case, we use electrostatic interactions that you can align this kind of buildings block in well-defined structure for functions. Or we have what we call hierarchical self-assembly. In hierarchical self-assembly, we will start to have buildings block, and this buildings block to build nanostructure. And this nanostructure, it works as an intermediate, as a buildings block to higher structure. And this higher structure can use again as a buildings block to make higher and higher and higher structure. This is quite not easy concept. This is quite complicated. If you're putting more different level of complexity, different types of driving force, you do need to understand how complexity it works, which driving force is more dominant than the others that you can make well-defined structure. The whole essence behind it, we like to make nano-structured material, can make multi-functions, can use in different functions in. We do have in nature, this is shown, this is already done long time, or I mean it is established system in nature. We can learn from it, or we can make what we call it man-made devices. This is in our lab. We can align structure in different level, as you see here at the air solid interfaces, or we can make vessel-like structure. At the end of the case, what we're looking for in principle, we're looking for molecular buildings block. We can use different models, could be polymer, dynamers, peptides, surfactant, and so on. And the important part which we have to understand how the driving force it works. One complicated system to understand more about self-assembly to design your system with this kind of building block, and you can see how this driving force it works, how the mechanism can take place that you can build well-defined structure. In my concept, I am putting two different walls together, what we call it inorganic plus organic, that we can have hybrid material. The organic parts can give you more hint about flexibility, processability, that you can have self-assembly in it. In this case, we can use different building blocks, different models, polymer, polymer, and so on. Or we can combine the inorganic inside the polymeric matrix or the organic matrix, that we can have more functions in. We can use different concepts, gold, silver, magnetic material, semiconductors, and all of this. The whole essence behind it, bringing these two types of material to make hybrid material, we have what we call it function material. At some extent, we using bottom-up approach by using or via self-assembly process. One disadvantage about self-assembly, you can have what we call it defects. To minimize this kind of defects, to have well-defined macroscopical structure, we do need to use at some extent what we call it external field. Why is that? That we can improve the well-defined structure to have it mesoscopically, macroscopically, and so on, to use it from functional material into multi-functional material for devices. This is our aim or ultimate aim for our research, what we're doing. This kind of nanostructured hybrid material can be used in huge number of applications. We can use it in medicine, diagnostic tools, we can wounds tissue repairs, in self-healing material. We can use it in different kind of energy, photovoltaic, photocatalytic activity. We can have more application optics. We can switch the hydrophobicity of some surfaces from hydrophilic into hydrophobic, or we can use it in data storage, flexibility electronics. This is a new generation of the devices what we having. I start my career a long time ago. Therefore, we're working in different kind of models, self-assembly models. We work in 1 and 2 and 3D structure. We work on copolymer, dynamers, biopolymers. We having decent track records in this area that we can think about organic, inorganic, hybrid material by using polymeric, dendritic, and so on. And we can template in situ approach different level of inorganic material. As I mentioned before, self-assembly is powerful tools that can be used for manufacturing the new generation of nano devices. However, it's not easy topic. You can, if you're using self-assembly, we have to think about which kind of material, which kind of substrate you put your material on. Are you going to work in wet chemistry? Which kind of inorganic filler are you going to use? Which kind of methods? How the viscosity looks like? Architectures. There are many other parameters we have to understand that we can really start to build different level of devices in. As I mentioned, we work in different level. We work in 1D structure that we can having different level of alignment of structure. We work in 2D structure that we can have alignment of 1D structure in 2D or two-dimensional level. We have a honeycomb structure. We can switch the hydrophobicity of different surfaces, or we work in 3D structure. As you see, we can have this what we call it lamellar structure between polymeric structure and inorganic filler inside this 3D structure. This is really interesting type of structure, can be used in optics and optoelectronics in different level. Today, I'm not going to speak about 2D or 3D. I'm going to consider more likely about 1D structure. Therefore, I will try in the next 4 short stories to convince you that self-assembly is a powerful tool for our next generation of devices. The first story, I like to introduce you polymer. It is a very interesting type of polymer, just based on 2 polymers or more connected together with a covalent bond. These two polymers does not like each other. They start to make what we call it microphase separation. And this is quite very interesting kind of material that you can start due to just aligning or change the volume fraction between these two polymers, that you can have a variety of structure in. Of course, you're making more complicated morphology of block copolymer. You can have grafted copolymer, you can have triplock copolymer, making story more complicated. We can even think about star copolymer. All of this kind of models of block copolymer can make self-assembly. You don't need to do anything, just you adjust your materials, you put it together, you can have accessibility in different level of structure. We can think about what we call it spherical-like structure, that you can have it here, cylindrical, aligned in hexagonal structure, or gyroid or lamellar structure, that you can have this level of structure. Right now we speak about polymer. However, we're looking for inorganic filler inside the polymeric matrix. We make a very interesting model for it, polystyrene polyvinyl pyridine, and we use the chance in chemistry. There are a very nice link between these groups and inorganic precursors, that we can use this self-assembly process, that you can align the inorganic and well-defined structure by using the self-assembly of the block copolymer. This is a whole story about it. This concept is flexible. We can have wide range of materials. We can induce for sure multifunction material. As I mentioned, we can have spherical micelles in it, cylindrical or vessels, or different level of 3D structure. The whole concept about polymer, we can connect this polymer with inorganic material. As I mentioned before, we have accessibility for noble transitions metals, or semiconductors, or magnetic material. As you see here, we have plasmonic. You can see different level of optical properties, or we can change the fluorescence due to the inorganic semiconductors nanoparticle, or we can control different level of magnetization by using different type of magnetic material. As you see, there are this kind of functions. Putting in well-defined structure can make really difference, or component that you can use in different level of device. We done this simple structure. We have block copolymer. We put inside the block copolymer in what we call it selective solvent. We put the inorganic inside one of the polymer. We will have what we call it cursal structure. The cursal structure having in the core the inorganic functional material. As we mentioned before, it could be noble, it could be semiconductors, it could be magnetic material, and this is quite coated with different level of organic matrix. As you see here, we can see the atomic force microscope, that you can see 0D structure of cursal structure aligned in 2D levels, that you can see the inorganic inside coated with the polymeric structure. The good news is that we can control the distance between these inorganic particles, that we can vary, or we can have accessibility in many level of functions. We can control the level of the inorganic, we can control the distance between them, we can control the alignment between them. Just you can change the polymeric length and the volume fraction between these two different polymers in the block copolymer. This is quite interesting. We like not only to make what we call a 0D structure, we like to make it from 0, or go from 0D structure in 1D structure. This is the title of our talk, and we make it very simple concept, that we can add extra solvents, that we can expand or swell this level of structure, that we can have it in 1D structure, or even we can make not only nano rod or nano wire, we can make ring-like structure, or we can have vessels on it. Simple concept that you can mix things together very quick. You can have the structure what you're looking for. We make different studies on it, that we can see how this block copolymer it works, and how the structure to make micelles in different shape. We can control in different levels, spherical, non-spherical, and so on. And this can make a well-defined structure be controlled in different level. If we like to make devices, we have to control quite well how the structure looks like. We use different parameters here, that we can use the volume fraction between the polymer, the volume fraction, polymer, and the solvent what you're using here, that we can move from spherical into 1D into very high 1D structure. As you see, there are nano objectives or nano root-like structure. You're having the inorganic filler inside the polymeric matrix, and this is quite very interesting, contrasting in the micrographs or transmission electromicrograph. Confirm this is a really well-defined structure, and all of this happened by using just self-assembly, nothing else except it. That was the first story, or the first short story. I like to go from the first into the second story, which we're using dendrimers. Dendrimers is one of my favorite polymer, or what we call it, polymeric matrix, but in well-controlled manner, that you can see in dendrimers. We have polymer with very high sophisticated molecular weight, that you can exactly see which kind of molecular weight. Therefore, dendrimer is this kind of polymer, but it is well controlled. In polymer, you can have what you call it a little bit polydispersity, but in dendrimer, it's well-defined molecular that you can work on it. Having what we call it high or large number of functional group, and you can see it's a different generation. You can have it smaller, generation 0, or bigger, a little bit, 1, generation 2, 3, and 4. And interestingly, things about dendrimers that you can having inside here, you're having a very nice cavity. You can be used in different level of structure here. Therefore, in dendrimers, it's well-defined molecules, have well-defined architecture, can have monodispersed molecular weight, high number of functional group, as I mentioned before. We have a very nice cavity inside that can be used for different application, and of course protected core environment in. It is quite very interesting type of polymers, and the most interesting things, if you can add it more function in by adding what we call it the inorganic nanoparticle in, that we can use different level of functional, metallic, magnetic, and semiconductors in. Interestingly, things about dendrimers is this could be done everything in different media. As you see here, we can use dendrimers as a reactors that we can control different level of growing mechanism inside the cavity of the dendrimers, or we can adjust the charge around the dendrimers that we can have different level of structure. As you see here, if you're using a very small generation, you can have generation 2, for example. You can have a very nice aligned nano particle, in this case inorganic nanoparticle, gold nanoparticle, or we can use higher generations that you can having instead higher or bigger size of nanoparticle. You can have a smaller, and as I mentioned before, dendrimers, according to the generation, we can change, or we can have different mechanism of the growing inorganic within the dendritic matrix. Mentioned before, we have dendrimers have a unique properties, have large number of what we call it charge, and the good news is we can switch this charge, that we can just use it as a building block, that we can have large number of nanofibers with very high aspect ratio. As you see here, we have the dendrimers. We can put different generation. We looked different level of inorganic. In this case, we use cadmium, and I will tell you later why we use this kind of inorganic material in, that we can have this very nice wire by using one metallic structure, in this case cadmium, that we can have a very high structured inorganic, which in this case cadmium aligned across this what we call as the fiber structure. This is micrograph of transmission electron micrograph, can showing you even in high resolution how the inorganic aligned inside the dendritic matrix. That was quite a very nice start. After a while, we thought we having fiber based on one metallic structure. We like to use or we like to produce fiber by using bimetallic structures, that we can have two different type of metal in one fiber. We're using the first fiber as a scaffold for the second. In this case, we're having a gold, and we can see we manage that we can put the gold
building block or nanoparticle across or along the fiber in discrete manner, as you see here from the high resolution transmission electron microscope or the image of the atomic force microscope. We having inside here the first metallic structure, and after that we put the other metal in. At the end of the day, we managed to have nanofiber by using dendrimers with two different types of metal structure on it. Of course, we like to work more about how it works, how the mechanism. We found that this different level of inorganic can work in between the two dendritic structures, that we can have a very long fiber, as I showed you. As I mentioned, it was behind that, it was a reason why we're using cadmium. Cadmium is very nice type of material that we can be used as a precursor to make a semiconductors nanoparticle. In this case, we use cadmium as a part of cadmium selenide to have this inorganic nanoparticle. You can see the fluorescence is very nice, that you can have a very nice, with very high aspect, nanofiber based on semiconductors nanoparticles. We done exactly the same. We use this semiconductor nanoparticle as a scaffold that we can add another kind of metallic structure, that we can have metallic semiconductor together. And as you see, in semiconductors before, we having a very nice fluorescence. After we putting the other metallic structure, we change the fluorescence. We can quench it in different level, as you see here. The good news is that we having the bimetallic structure. Inside we have the inorganic semiconductors, and outside, as you see here, we having the another metal aligned in discrete manner on the one fiber structure. That was the second story. After block copolymer dendrimers, we saw this is quite polymer, quite sophisticated level of architecture. Dendrimers even more sophistication, it need more chemistry in. We try to make 1D structure by using a very simple concept, by using very short surfactant N. We use the same concept, what we call it in situ approach. We're having a very, very small surfactant. We use it as a starting material to make what we call it a gold nanoparticle, and we having here two function groups that we can align this gold nanoparticle in a well-defined way by using just very simple hydrogen bond N. We use two mercaptan ethanol that we can use in situ approach gold nanoparticle N, and we can having this kind of nanostructure in well-defined way. Atomic force microscope confirms that we can have spontaneously linear self-assembly by using in situ approach, that we can having this fibril-like structure. We make different level of structure, as you see from the atomic force image, that you can have different architecture of this 1D structure, gold nanoparticle inside this very short surfactant N. It is quite interesting that we have the fiber, or we align this very small surfactant in fiber-like structure, but our aim that we can adjust the distance between this building block or this inorganic building block, that we can have well-defined structure in 1D. As you see, this is quite the distance almost the same. We have a very nice histograms can show the diameter of this particle is in well controlled, and you can see we can use this in optical on photo or optoelectronics, that you can control the unique properties plasmonic from gold, and you can see the distance well controlled, that you can control the electric properties behind it. We use different ratio of precursor, our inorganic, that we can have moving from particle into different level of diameter of 1D structure, and in fiber here, this is well controlled manner. If you have such structure built on hydrogen bond, we have to work more about how the structure looks like. If you're having temperature, how the key characteristics, how to influencing different level of structure, and you can have different thickness. You can prove the dominant driving force here. It was more likely the hydrogen bonds, that you can influencing the hydrogen bond just by what we call it temperature, that you can assemble and disassemble the structure in different way. We study not only temperature, we study the pH. We can see we can disassemble the structure from fiber into particle, into different size of the particle just by changing or simply change by the pH. That was the third story about surfactants. That by means we move from polymer dendrimers into very short surfactants. This is for material scientists, but what about material for biology or biological application? We thought a lot about this kind of structure. We managed to use or to make hybrid material based on elastin-like polymers, or something like protein. Elastin-like polymer is very interesting kind of protein structure or biomacromolecules. It is genetically engineered by using what we call it replicate DNA technology. Biocompatible type of material have a very unique mechanical properties, can be used as a smart material. This is a very interesting kind of biopolymer based on blocks of amino acids. And what we try to do, actually, we try to switch one of these amino acids inside this biopolymeric structure that we can have different level of self-assembly. We have this very interesting type of amino acid blocks inside fibril structure. We try to use in situ approach that we can have what we call cursor structure. We have inside the inorganic coated with the outside organic. In this case, we use a precursor, cadmium. I will tell you later on why it's cadmium. And in this case, we make this different cursor structure. And as I mentioned before, we change only one amino acid that we can charge it. We like to induce what we call a driving force. In this case, we use what we call it electrostatic interactions. We put this together that we can have the nanofiber based of hybrid material, organic, inorganic. The organic, this is elastin-like polymer. The inorganic, this kind of metallic structures that we can have this fibril-like structure. As I mentioned before, in this case we use cadmium. The cadmium is very unique that we can, as a what we done in Denmark, that we can use it as a precursor to make inorganic semiconductors. We can align the protein fiber by using different pH. We're starting from acidic more into neutral. That we can see in neutral we're having a very interesting kind of 1D structure based on elastin-like polymer coated inorganic semiconductors. It is very interesting to have semiconductor nanoparticle. It is having a very unique level of fluorescence. However, this kind of material is very toxic. And the essence behind all of this study is that we try to use toxic material in biological system. By means, we having a very toxic material, have a very unique optical properties that can be later on used in biological system. We start to work a little bit on the structure that you can see in different level of structure. We started with cursor structure, changing the pH that we can have a fibrillary-like structure, as you see from the high resolution TM. Interesting things, we like to adjust the buildings block and the distance between this kind of particles, that we can have a discrete distance between them, that we can propagate different level of collective properties between this kind of semiconductor nanoparticle. As I mentioned before, the whole aim about it is that we can use very toxic material like cadmium selenide. We put it inside polymeric matrix that we can use it in biological system. This is our control here. Cells here or cell test can see the survive in control. Material alone without any kind of coating with this elastin-like polymer, this is pretty toxic. Only 25% of the cells survive. Nevertheless, if you just coat this kind of semiconductors with this elastin-like polymer, that you can see the surviving rate is pretty high, that you can really use this kind of high fluorescence type of material in biological system, and you don't worry anymore about the toxicity in. This is a picture showing that if you're putting this kind of material inside biological system, that you can see it is still intact and having a well-defined fluorescence activity in. that was my first story. I hope I convinced you that is self-assembly or directed self-assembly is a powerful tool to make nanofabrication. I show you different models between or by using different kind of buildings block, organic, inorganic. We make 1D structure, we make gold nano wire, we're making semiconductors, we're making different level of structure here. I thought that was quite interesting to give you a new approach about self-assembly. And actually self-assembly is not new, this is actually coming from nature. And the message, I really like that to give it to you today, that we have a lot of things to do with nature. And there are a long way that we like to learn more from nature, which having self-assembly as a well-established concept, just what we're looking for, we mimic this concept or mechanism which working pretty well in nature and living organizations that we can learn a lot about it. Therefore, nature and living organism is the best school that material scientists can learn from it. I like to dedicate my acknowledgement to my research group. This is actually old picture from my time in Nottingham. All of this work, I cannot do it alone. I have a very active young scientist. They done all of this kind of work between Germany and the part of it done recently in Germany. This is actually, I like to thank the group. I like to thank the financial support during my time in England from EBSRC due to Nottingham Innovation Manufacturing Research Center, and of course PMBF, German Funding Society, and DAD for their funding. And at the end, I like to thank you very much for your kind attention and the kind invitation. Thank you.
Thank you very much for interesting lecture. And now the questions. Maybe audience has questions, please. I encourage participate actively. Actively,
I'm
please.
very happy to answer any question.
Thank you very much. Very interesting, of course. Too. I would like to have more questions, but start with one. You use metallic, for example, gold, nanofiber. What is the application? Why I ask you? Because if you use material bulk, what is called usually, or nano, different conductivity. Therefore, low and low diameter this fiber conductivity decrease.
Yes, thank you very much. It's really a very interesting question. Maybe I didn't explain quite well. 1D structure is quite interesting. You're having a huge surface area. And what we try to do, we make structure in structure. I put a big emphasis that we can make fiber or we can make 1D structure, but we was quite keen to align the gold nanoparticle inside the nanofiber with discrete manner. In this case, you can give more chance for electrons that can hop or tunnel. And we found that really there are well-defined distance can really induce these unique properties on. One important issue about nano device, nanotechnology, what you call it wiring. You can have a very nice component, but we do need to wire them together or integrate them together that we can have a function on it. And due to my research, I try to find a way that you can make this kind of connection, not only with normal 1D structure, but it should be the inorganic, well-aligned inside the polymeric matrix. With this way, you can really have a well-defined control on the properties. Did I answer a question?
Maybe not.
Okay.
Other questions, please. The first question was about limits for miniaturization.
Yes, yes. Physics certainly catching to the limit, for sure. Right now we're using what we call it photolithography, or we're using different concept. still lithography that we can having this nanostructure. I think, correct me if I'm wrong, that the next generation we should move from this limitation of physics, diffraction limit, that we can go into self-assembly. You can go really with self-assembly as I show you here. We having 2 nanometer distance between particles. We can have it in long distance way. I think if we like to go more in multifunctional component, smaller device, we are eager about that. Everyone like to have a very small smartphone doing everything. I think the next generation should be using manufacturing concept based on self-assembly process. I don't know when it comes, but I'm pretty sure it will come someday.
And one limiting factor will be the moving part. Moving part in these devices is electron.
Yes.
But in mechanical devices, something other.
Yes, yes. If we think about hybrid material or composite material, it's quite interesting. Today I show only 1D structure, but we work in 2D structure and 3D structure. Can you imagine we started from bottom-up approach, that we can really starting from particle beside another particle in very thin film, putting the next layers, again polymer, the next, that we can have well-defined, aligned, macroscopically aligned structure in 3D. This is really having a significant impact on the mechanical properties. In this case, you're having electronic, optoelectronics, maybe optics. You can use it as what we call it configurable crystals or photon crystallic structure. And parallel, you enjoy this mechanical stability of this kind of structure. This is the essence behind it.
Okay. More questions? No questions? Oh, yes. Yes.
I would like to ask you about definition, because we're working with self-assembly too. But usually we told if we control this, like you show us different shape of the molecular organization, it means not self-assembly. You control by temperature, by magnetic field, electric field. What do you think about this? It is very important, it seems to me.
Okay. That is a very fundamental question. It's very hard to answer. However, I will try to give my answer in it. Self-assembly is a very complicated, complex methods to work with. To start to work in self-assembly, we have to see first from nature how it works. We try to understand it, and then we try to apply in it. Nature, it works in very high sophisticated way. But our problem is, if we try to go from simple structure based by self-assembly, it could be makeable, we can do that. However, if you're getting more complex structure, you're involving more driving force. In this level, we actually quite lost. We don't know which driving force will be more dominant to direct the structure. And for this reason, it is not easy to make highly macroscopically aligned structure. We have always defects. At the beginning of my lecture, I say, okay, we're having a nice self-assembly. We can put this self-assembly in well-controlled, what we call it, external stimuli, that we can avoid these defects in it. Right now, as a human being, we can do self-assembly. We try to make the structure with very cheap way as a manufacturing methods. We try to control more the parameter, which you see, okay, self-assembly nature can make spontaneously, reversible. But if we like to learn from nature, we have to put the touch of the human being. Our touch is just to dedicate the parameters that you can really improve the well-defined structure. Complicated system need more understanding, fundamental understanding. That is how we should make more research needed to use this method as a powerful tool in next generation of devices. Really very interesting question. I hope I try to answer it as much as I know.
Maybe not not for everyone.
Yes.
Maybe,
We have to discuss
after
it.
your lecture.
Yes.
I have more questions.
Yes.
Questions and other questions, please? No questions? Thank you again for your lecture.
Thanks a lot.
The floor is going to Eva.
Thank you
Thank
very
you very much.
much
Okay.
for a very interesting lecture. Thank you.
Thank you very much for the nice gift and the nice invitation. Thank you.
Thank you. And now we will continue with the presentation of Dr. Drunka. But before, I would like to introduce you to him. Reinis Drunka started his studies in chemistry at the University of Latvia in 2005. He has more than 10 years experience in science since 2008, when he started to work for Riga Technical University. In 2014, as a PhD student, he started to carry out research in the field of synthesis of nanomaterials and of visible light-active photocatalysts of the basis of TiO2. Since 2014, Mr. Drunka has also been head of the company Plasma Ceramics Technology, and the main fields of the company are operation and production of nanopowders through plasma technology and scientific work in the development of new technologies. In 2016, Mr. Drunka started to work as a lecturer for master students, leading also laboratory projects in nanochemistry. In addition, since 2016, Mr. Drunka has been a member of the Latvian Materials Research Society and the head of the Technical Ceramics and Nanomaterials section. He has participated in various research projects of Latvia and also EU funded projects, and on 15th of November, Mr. Drunka defended his doctoral thesis, and now he's here and the floor is yours.
Thank you. Dear ladies and gentlemen, my name is Reinis Drunka. Today I will give a short introduction in our research, synthesis and properties of modified titanium dioxide photocatalysts. I guess all of you already has heard or read in newspapers that there are problems with fossil energy sources. The consumption of those materials are increasing every day, but they will last. The resources will last only for few decades. So we have to think about some alternative energy sources, and we need to think also about environmental pollution problems, how to make world cleaner. So the solution would be multifunctional materials that can be used for solar energy conversion into other energy types. And for this application we need specific materials, photocatalysts. So what is photocatalyst? Photocatalyst is a material that under the influence of light can make chemical reactions go faster. And in this process, this material don't change his chemical composition. Unfortunately, currently known photocatalysts are not so active for those applications, so we need to find new materials for those applications. Some words about photocatalysis process. This is a simple mechanism of this process. We have sunlight or other light source. When our photocatalyzed surface is in contact with light quants, electrons can be transferred from valence band to conductivity band, and holes can be produced. Electrons and holes can attack with oxygen and water molecules that are in contact with material's surface, and those molecules can be split into free radicals. And these free radicals can, let's say, attack in other chemical reactions. In our case, they can degrade organic pollutants. So why do we use titanium dioxide? It's already well known since 1972 that this material can be used as photocatalyst. Some decades later, researchers have discovered that this material also have hydrophilicity phenomenon. Also, this material can be produced in form of nanomaterials. This means that materials can be with extra high specific surface area, and this material is really cost efficient and safe material. We use it as a white pigmentary and let's say in cosmetics, in food industry, so it's quite safe. But as usually, there are some disadvantages with materials, also with titanium dioxide, due to its large band gap. For anatase, it's 3.2 electron volts. It cannot absorb sunlight in visible light spectral part. It can only absorb ultraviolet light. But as we all know, about 44–45% from the light we get from sun is visible light. So we have to find some materials that could be used in this spectral part. And there are some possibilities to improve properties of titanium dioxide. As I already told, one of possibilities would be to make various morphology nanostructures with high specific surface area. It would be porous materials, fiber materials. Another possibility would be to make some modifications of the surface of those nanostructures with various modifiers that can reduce the band gap of titanium dioxide. And also for industry, it would be much easier to work with photocatalysts that are fixed on surface. So we don't need filtration process after this photocatalyst process will end. So the aim of our research is to find optimal methods how to prepare nanostructured titanium dioxide, to improve them to be used in visible light, and to compare various modified photocatalysts in the same conditions, and to give some recommendations for application of obtained nano photocatalysts for solving environmental problems. So, and we have chosen a list of modifiers here to test. And we have tested them in ultraviolet and visible light irradiation to degrade methylene blue solution. For material characteristics, we were used scanning electron microscopy for morphological analysis and particle size determination. Also, transmission electron microscope was used for morphological research. Nitrogen absorption method was used for specific surface area calculations. Phase composition was detected with X-ray diffraction method, and chemical composition was analyzed by using X-ray fluorescence spectrometer. So the first method for obtaining nanostructures was chosen anodation. It is an electrochemical method, so we use titanium fall or sheets. The second electrode is platinum. We have electrode containing fluoride ions. The second part can be also other, let's say, electrolytes, but it is important to have fluoride ions here. We have tested various experimental durations. The best results were with 30 to 45 minutes experiments. The power was DC, 20 volts. The next method was plasma electrolytic oxidation method. Also we use titanium foil. The setup is quite similar to the anodization method, but we use much higher voltage, and the experimental time is much shorter. So we have noticed that when we choose 160 volts voltage, we can obtain the best quality of such titanium dioxide nanoporous coatings on the surface of titanium dioxide. And in this picture you can see small sparks, spark discharge during this microplasma electrolytic oxidation process. It is the titanium electrode covered with such sparks. So, and the third method was microwave assisted synthesis method. It is some kind of hydrothermal synthesis method. So we use closed volume, we heat it up, and we get a pressure inside this volume. So in our case, the holding time was 1 hour, temperature 240 to 245 degrees. This was the optimum for nanofibers. In such case, we obtain nanofibers with the best quality, and the nanofibers are located on the surface of this reactor chamber. So we can remove them after the process. Here you can see obtained nanofibers. This is a petri dish where we can put the nanofibers on it, and those pictures are already under huge magnification in scanning electron microscope and in transmission electron microscope. As you can see, we have good orientation of those nanofibers, and single nanofiber can have a diameter starting from 5 nanometers. So the photocatalytic activity was measured by using metal and blue degradation method. It is an ISO standard method. So the absorption is controlled with spectrophotometer at the wavelength of 664 nanometers. And during this process, such a blue solution becomes transparent, and we can calculate the concentration of it. So we also have tested our samples after the synthesis process to find out what chemical phases, what material phases we have in this material. So if you look to titanium dioxide nanopore coating, you can see that here is also rutile phase. It's because of the temperature during the synthesis. In other cases, the main phase is anatase. In nanofiber case, we also have some monoclinic titanium dioxide phase. For modification, we have chosen 3 main methods. The first one is chemical deposition method. The second one is electrochemical deposition method, and the third was calcination method in modificator containing gas flow. So, and after synthesis, samples were calcinated in various temperatures because of their different physical and chemical properties. So, here are morphologies of our obtained modified titanium dioxide nanostructures. Here you can see nano tube coating. For this sample, it was typical detector used. For these two samples, we were using backscattered electron detector that allows us to see our dopants or modificator particles, so we can see them better. And here you can see one sample modified with 1% of gold nanoparticles. As you can see, gold is in form of some crystals, and with crystalline size 10 to 25 nanometers. So here is a summary of properties of titanium dioxide nanofibers modified with various modificators. As you can see, after synthesis, pure titanium dioxide nanofibers are with extreme high specific surface area, but after calcination, after modification with modificators, this surface area decreases, but still we have almost 2 times bigger than this surface area than our raw material titanium dioxide nanopowder. So, and here you can see some part of results for titanium dioxide nanofibers modified with various modifiers under UV irradiation, under visible light irradiation. As we can see, the activity in UV light is much higher than in visible light, and materials can increase activity of titanium dioxide nanofibers in following order: europium oxide, silver, palladium, sulfur, platinum, and the most active one is gold. So for us, the important graph is this one, because it's in visible light, and this is what we are looking for. Here you can see the same graph, the same measurements, but we are testing nanotube coatings, and the experimental times are 3 times longer. So this means that our nanotube samples are not so active as nanofibers were. So, and here activity increases in following order: wolfram, tungsten oxide, sulfur, palladium, platinum, and the most active one is gold. And the third graph, here you can see the same photocatalytic activity measurements, but for nanoporous coatings. And also here you can see that this activity is not so high if we compare it with nanofibers, but still we have good activity in visible light for sample modified with gold. So where to use such materials? We have tested those materials for degradation of organic organic pollutants that could be useful for, let's say, wastewater treatment. We have tested also these materials in field of glycerin oxidation. This is important in biodiesel production, and also materials that are modified with europium oxide are luminescent materials, and they can be used in, let's say, light emitting devices. We are planning to make some further researches in water electrolysis and hydrogen production, conversion of gaseous products into less harmful and industry usable compounds, and we would like to try also to make some gas sensors. Yeah, as I already told, we have good collaboration with Svetlana Chornaya, Professor Svetlana Chornaya, Institute of Applied Chemistry, Riga Technical University. She has tested our photocatalysts in their application for glycerin oxidation to glyceric acid, and the selectivity reaches 76% for 100 glycerin to glyceric acid conversion. So those catalysts are quite good for this application. So some conclusions. The main one is that if you have some samples with the same modificator amount, the activity increases in following order: nanoporous coatings, then nanotubes, and then nanofibers. And if we are looking to compare nanofibers with nanoporous and nanotube coating samples, then it was noticed that 0.1 gram of modified titanium dioxide nanofibers can degrade the same amount of methylene blue per hour as similarly modified titanium dioxide nanotubes or nanoporous coatings with surface area 1 square centimeter in 3 hours experiment. And it was measured that photocatalysts that are modified with precious metals can degrade up to 45% more methylene blue solution than pure nanostructures, and up to 14.6% invisible light irradiation. So thank you for listening. Your questions, please.
Discussions? No questions? Yes.
You mentioned that one of the problems with titanium oxide is that it has a very big energy gap.
Yeah.
And that it could use it in the light, visible light. Have you checked the energy gap of the sort of compounds that you made?
We will do this in next step. Yeah, we have to think about it, but we don't have equipment in our laboratory to do this. So we will.
Another questions? Please.
I would like to ask you about your method production titanium oxide. You used three methods. Did you study this method about the phase titanium oxide?
Yeah.
Influence on the photocatalytic properties?
Yeah, we have think about it because as you may know, the commercial titanium dioxide that is usually used as a standard is this P25 nanopowder that contains also anatase and rutile crystallic phases. So we are trying to also work with combinations of those two phases. I already demonstrate that in this titanium dioxide nanoporous coating we have those two phases together, and also in nanofiber case we have such monocline titanium dioxide phase discovered, so we have some mixtures here. It's not a pure titanium dioxide anatase.
Please.
Thanks a lot. Really very interesting catalytic activity of titanium dioxide. My question about the size and size distribution. You spoke about particle and fiber. Did you just consider if you're having monodisperse or polydisperse or different diameter of the fiber? How is this influencing the catalytic activity of the titanium oxide?
our let's say our research was to obtain these titanium dioxide nanofibers with higher specific surface area. So we tried to adjust these regimes for microwave assisted synthesis to obtain nanofibers with high orientation in this coating. So, but we haven't let's say analyzed till now diameter influence to photocatalytic activity, because it could be quite hard to do this.
Thank you.
Oh, I have one question. We have many semiconductors with the appropriate energy gap, 2 to 5 electron volts. Do they also have photocatalytic activities or not?
Some of them have, some of them don't have. We have tried to work also with tungsten oxide. We have tried to combine those two materials, but unfortunately it's not so high activity as we were expected.
Thank you. Yeah, one question, please.
Yeah, I would like to ask you about modification.
Yeah.
What is modification? Usually you use these atoms, for example, gold, as impurities. Yes. Did you compare black titanium oxide? You maybe know what is black, with your method modification or impurification photocatalytic properties. For example, you told 40% is the case of black titanium oxide in literature.
Yeah, I have read such research, but we haven't compared it with such material.
Cool.
Yeah.
Of course. Thank you again for
Yes, thank you for your contribution, Dr. Drunka. Thank you. Thank you all for coming today and joining us. And now I would like to invite you all to continue discussions in more informal way with some cup of coffee or tea here outside the room. And I also wanted to say, if somebody have applied for a certificate, then you can get it from me, and please fill the evaluation sheets and give it to me or to the registration colleague. Thank you for your attention.